So those were both scenarios without friction. So let's go ahead and let's do some with friction. So I'm going to make these ones, the scenarios get a little increasingly harder. So let's try one that's a little bit more different, a little bit more difficult. So let's see if I can draw a triangle. I'm going to make this one a little bit bigger. Hey, not bad. Okay. So let's say that you have a box, and this box is being pulled up the incline. Let's say that's what's happening. Let's say that this is a car, and we are trying to tow it up the incline. Here is our rope, and it's being pulled up the incline. There's like a little wheel right here. Okay, and it's being pulled up the incline. All right, I want to know what the net force is on the whole system. Okay, so this is a car. So let's write the question. A car, not the car. A car. A car is pulled up a slope. Let's say 12 degrees. The car weighs 3,000 newtons. If the coefficient of friction is 0.3, what is the net force on the car? All right, so now there's a little bit of new information here. So I haven't talked about friction yet, okay, and it's fairly simple, okay? We've talked about friction in terms of, abstract values. I haven't really talked about how to calculate friction. So basically this is how this works. So friction depends upon two things. Friction depends upon type of surface and the force on that surface. Okay, so that's actually reflected in the equation for friction. So frictional force is equal to the force applied to that surface times what's called the coefficient of kinetic friction. Now I know that looks like a ridiculous M. Let me draw this better. The force applied to that surface, and so that is a Greek letter mu, and so frictional force is equal to the force applied to that surface times the coefficient of friction of that surface. So basically this is the force here, and this is the type of surface. Now there is a numerical value for surfaces. Now the coefficient of friction is basically how much friction do you have going on between two surfaces. If you put two pieces of sandpaper together, friction is going to be huge. If you put two blocks of ice next to each other, the friction is not going to be nearly anything, okay? But those values are always under 1. So if you ever see a frictional value over 1, something's wrong. Frictional values are always under 1, so they're always like 0.15 or 0.3 or 0.7 or something like that. So this one is 0.3. Now, when we do this in an inclined plane, this equation will look slightly different. This label right here will say something different. But this is the same. So this actually stands for the coefficient of friction of kinetic friction. That's what the little k says. So I'll call it mu sub k because this is the Greek letter mu. But mu sub k is the coefficient of kinetic friction. So that's going to be moving friction. If you ever see one that says this with an S, that's the coefficient of static friction. So that's when you don't have an object moving. You're still going to have friction on an object even though it's not necessarily moving because that's what's keeping it from moving. Okay, so let's get into this equation. Okay, so let's highlight some pertinent information here. We have 12 degrees, we have 3,000 newtons, and we have 0.3 coefficient of kinetic friction. All right, so let's draw the free body diagram for this. Gravity acts on everything, going straight down with gravity. Perpendicular to my surface is normal force. Straight down from normal force is going to be Fg of y. And going over there is going to be Fg of x. Okay, and then we've got our angle theta out here. That's going to be 12 degrees. Theta is the same in here, so that's 12 degrees. This is 12 degrees. Okay, so now we can do this here. So this being pulled up is a tension force, so Ft, because it's tension of a rope. And so we still have, we are going to have net force going up. We know that the net force is going up, so I'm going to draw that here. And then we have Fg of x that always goes down the slope. Okay, that's this one here. Fg of x always goes down the slope. And then we also have frictional force this time going down the slope. Okay, so there's quite a few things that go into this one. So let's start writing this net force equation. So F net is equal to, so let's look at all these values. So we got all of our values in one spot. So this way I'm not worried about. It's these that I'm concerned with. So F net is equal to, so we're not going to use that one because we're equaling everything to F net. Tension force minus these other two because they're opposite. Okay, all we have to do now is calculate. Okay, I've realized that I left out a value, so sometimes when I make my own problems, I leave values out. So I left out tension force. So tension, so I'm going to add this to the question. Tension on the rope is, let's see, we're pulling a car. So let's say, let's say 4,000 newtons, because you're pulling it up an incline. So let's say 4,000 newtons is my tension on the rope. So that goes into net force. So F net is equal to 4,000 newtons minus my frictional force minus Fg of x. Now we've already calculated Fg of x, so we can do that pretty quickly. Fg of x is equal to mg sine of theta. Fg of x, our weight is given in newtons, so that means that I can just go ahead and put 3,000 straight in. 3,000 sine of 12. So 3,000 sine of 12 is 623. Let's do whole numbers, that's fine. So Fg of x is 623 newtons. Now, this doesn't have to have a value because this is not my end answer. I mean, not a value. It doesn't have to have a direction because this is not my end answer. I'm only looking for a direction for your end answer. Now, here comes the tricky part. We have to calculate frictional force. Now, let's go determine how we're going to calculate frictional force. So frictional force depends on two things. The type of surface, which that's going to be determined from our problem, the 0.3 that was given us in our problem. So that was the mu sub k, 0.3 coefficient of kinetic friction. That's the first thing that you need for friction is the type of surface. Now we need the force on the surface. Now there is a value that we use when it comes to the surface, and that is normal force, because remember, normal force is perpendicular to the surface, and so that's actually how hard you are pushing on the surface. Now, we, if you remember, we don't have any x and y values for normal force because we calculate them all for Fg of x. So we are actually going to use Fg of y to determine the force acting straight down on the surface, which actually makes more sense because normal force, I mean Fg of y is actually pushing straight down on the surface. But it's got to be the value that's perpendicular to the surface. You can't use this value because this value is actually going down the incline. I need the one that's actually pushing down on the surface. And so that's going to be Fg of y. So let's go. Now this equation for frictional force is always the same with two-dimension motion. So frictional force Ff is equal to Fg of y times mu sub k. And that's it, okay? But the problem is we now have to go calculate Ft of y because I have mu sub k, so frictional force is equal to, I don't know Fg of y yet, times 0.3. I have to go find this value. So we're going to go calculate that real quick. Now, the formula that I'm going to use for Fg of y is exactly the same every single time. So I'm actually going to do it right underneath Fg of x because it's really, really similar. Fg of y, just like what we did for the x component of Fg, was sine. It's the same thing, but cosine of theta. So Fg of y, okay, so it's exactly the same as, hold on, I'm going to highlight this for you so you see it. See, this equation here is really similar to this equation here. The only difference is sine and cosine. And that makes sense because technically Fg of y would be the adjacent side to that angle we have theta, so it would be cosine because it's adjacent over hypotenuse this time. But just like we used the mg here, we're going to use 3,000. So we're going to do is equal to 3,000 cosine of 12. And so this equation for Fg of y is always the same. So let me highlight all three of these equations that stays the same no matter what. These three will always, always be these equations. The only problem is you don't always have to use them. So if you have friction, you have to use this one and this one if you have friction. If you don't have friction, then you don't use these two because these two are only for friction. This one you always got to have. Okay, but these two are only with friction. Now, let's go ahead and let's calculate this. Fg of y is 3,000 cosine of 12. 3,000 cosine of 12 is 2934. Okay. So we're getting there. We're almost done. So 2934 goes into here. So frictional force will be 2934 times 0.3, which is 880. Okay. So I feel like this is a lot of steps. Let's walk through what I have done before I get the final answer, because this is not the final answer. Because the final answer is supposed to be what is the net force. Okay, this is not net, this is not net, and this is not net. So we're not even there yet. All we had to do is go find these things. Okay, so we said that F net was tension force, which we had already from the question, minus frictional force, which we just found that one, minus Fg of x, which we found that one. Now, the reason why we had to do this is because in order to find frictional force, we had to calculate this one right here, which is what this is. That's why we had to do that. Okay, so now I can go and put everything into the net force equation. So 4,000 minus my frictional force, which is 880, minus my Fg of x, which was 623. So you just put that in the calculator, 4,000 minus, no, not times, 4,000 minus 880 minus, I forgot the other value, 623. Hit enter, you get 2497 newtons down the incline. Actually, no, it's up. It's up the incline because we're pulling it up, I forgot. Up the incline. All right. That's as hard as this is going to get, okay? That's as hard as this is going to get as far as net force, okay? The only other thing that will make this any harder would be how to get this to the acceleration, how much it's accelerating. So my question that we've done today was, what's the net force on the object? The next hardest question is going to be, what's the acceleration of that object down the incline? That's actually fairly simple. The hard stuff is what we just did. Okay, so please make sure you master this, because when we get to acceleration tomorrow, you will be lost. So I will review some tomorrow, because I'm going to have to do all of these steps over again. But please make sure that you're asking questions if you don't understand. Let me know if you need help.